So today's one of the bigger days of the course. We're going to introduce the concept of derivative. And so what you need to think about as I go through this is that calculus really is the study of change and rates of change. And when we think about a rate of change in math, we should be thinking about the slope. Like if you think of a line and we calculate the slope of the line, it's the rate at which a quantity is changing. So that's basically what we're going to talk about today. It's all going to be all about slope. So we're going to start with a picture. We're going to have a curve here, f of x. Maybe it looks like this. And we're speaking in generalities here. So now we're going to look at a point, a random point there, which we'll call x. It's at, we're going to call its x coordinate x. And then its y coordinate would be, well, if we plugged x into the function, so we'll just call it f of x. Remember, that means a y value. So those are the coordinates of that point. And we want to look at, really, the goal here is to look at what rate is the graph changing at that point. So a nice visual for that is to draw a tangent line. Now remember, a tangent line, thinking back to geometry, touches once. It touches a circle only one time. So it's going to hit the curve only one time in that area. That's called the tangent line. What our goal is to find, if we find out how much the graph is changing at that value x, what we want to know here is what's the slope of that tangent line. The problem is this: you only know points that are on the curve, and since the line only touches the curve once, we only know one point on the line. So you cannot find a slope only given one point. So let's recall our slope formula. I'll keep it up here for a second. It's change in y over change in x, or y2 minus y1. That's how you find the change in quantity, over x2 minus x1, right? So we're looking to do that. The problem is it requires 2 points. And we only know 1 point on our tangent line because it only touches the curve once. We're going to assume that we can get any point as long as it's on the curve. So like for instance, if I had this other point down here, I could find its coordinates, and I could do the slope of the line between those 2 points. So I'll draw that in like a blue. I could find the slope of that line because now I know 2 points on that line. That line is called a secant line. Okay, so that secant line touches the curve twice. And that's the definition, if you remember back from geometry. A secant line is a line that intersects the circle twice. So we're going to come up with the coordinates for that point. So what we're going to say is this x value, we're just going to say that we've increased that some random amount. We'll call it h. So this new x coordinate is going to be x plus however much we increased it by. That's our new x coordinate. And then the y coordinate is simply if we just take that x coordinate and we plug it in to our function. So that's what f of x plus h means. Right? Remember that this means the y value I get when I plug x plus h into my function. So now I've got I kind of have 2 points here that I can work with. And really the idea here is that while we can't find the tangent line, our goal is we want the slope of the tangent line. We're instead going to find the slope of the secant line and use that as an approximate slope for the tangent line. You agree that those slopes are somewhat close to each other. The slope of that tangent line there is negative, right? So that means that the graph is changing, going downward as I kind of move to the right, because if you have a negative rate of change, your quantity is going down. The blue line, the secant line, is also negative. So it's a good approximation. They're both negative, and you know, one of them's, you know, maybe they're like -1 and -1/2 or something like that. So we're going to investigate that a little further. But what we want to do is write out our slope of the secant line. So I'll try to keep this color coordinated here and do it in the blue. So the slope of the secant line, I'll say it's m of this secant, is going to be y minus y. So that's my y coordinate from the first from that point, minus the other y coordinate from the other point on the, there's my f of x. I'm going to get rid of those arrows because things could start to get confusing if I have too much drawn here. There's my change in y, y minus y, over x minus x. So there's my x coordinate for my point minus my x coordinate for my other point. That expression right there is going to represent the slope of the secant line. And this is kind of where we're going to start off. And remember that that's going to be used essentially as an estimate for the slope of the tangent line. So let's go down through here. What does that expression represent? We're going to say that f of x plus h minus f of x. I'm going to write it out again. It's good to get used to. You've already seen this a lot in this course because we knew it was coming. So we made you do it a lot. We called it the difference quotient, right? So that expression represents the slope of the secant line. And remember, slope, we really want to think of that as it's a rate of change. That's the whole goal here. Now it says, what does that expression simplify to? Well, I can make it f of x plus h. I can't simplify the top because these need to get plugged into the function first, right? And then I can simplify them, but I don't have a function because this is a general formula. So you're going to simplify the numerator when you do a problem after you've already plugged the stuff in. And like I said, you guys have been doing this already. But on the bottom, you can simplify it because those are just some x values. So x plus h minus x. The x minus x equals 0, so it ends up just being over h. Okay? So that's what it simplifies to. And we're going to see this a lot. Remember that this thing essentially means change in y over your change in x. It's a slope. All right, so now we're going to look at how can we make our estimate, our secant line, a better estimate to the tangent line? Well, we can just move the point a little bit closer, and you can see that the slope will the slope will get closer to the tangent line slope. So let's take a look at what this has. As h, the distance between the x values, x and x plus h, approaches 0, what happens to the secant line? So that means I'm going to pull that x value closer and closer to x. So this point's going to move along the curve closer and closer to our desired point where the tangent line is. What's going to happen to h? H is going to get smaller and smaller and smaller. So h is going to be approaching 0. So we'll say it this way. As h approaches 0, the secant line eventually, well, I want to say the secant line becomes closer to the tangent line. Eventually becoming the tangent line. Okay, what does the limit, so as h approaches 0, what does that limit represent? Remember, this means slope, And now if I find the limit as h goes to 0, that means eventually if I find that limit, it means that those 2 points, as this point, whoops, don't want the eraser. As this point gets closer and closer, eventually will lay on top of my desired point. That's when the limit, right? The limit as h goes to 0 means when you finally actually get there, it becomes the secant line. So this, the limit as h approaches 0 of that thing, represents the slope of the tangent line when x plus h, this point, f of x plus h, when that point finally becomes the same point as x f of x. All right, so we're going to stop here for a second, and I'm going to take a look. We're going to look at something in Desmos to help with this idea. So in Desmos, we're going to take a look at this idea. We've got 2 points here. Let me show you the tangent. That's the secant line. Let me show you the tangent line. Oh, that's the derivative. Tangent line is right there. Okay, so there's our tangent line. I put it in dotted white, right? So as I move this desired point, what we want is really the slope of the tangent line. So you can see that I can't find the slope of the tangent line. Let me turn off the secant line for a second. Because there's only one point that lies on the curve, and I can't find the slope of a line only given one point. And the only points we know are points that are on the curve because I can plug them into f of x to get their y coordinates. I can't just get a random point out there on the white line that's not also on the curve. So the issue is, how do I find the slope of that line? Well, we're going to use our secant line. So let me draw that back in there as an approximation. So right now, I see that the blue line is a good approximation of the white line in terms of its slope, how steep it is, right? They both have negative slope. What we talked about is the limit as h goes to 0. So as I move this point closer to the desired point of tangency, you can see what happens to the slope of the secant line. And what's happening to h is getting smaller and smaller and smaller as I move it in, because h is the difference between the x coordinates of these, right? So the x's are getting closer and closer together. You can see the slope of the tangent line is becoming a better and a better approximation. So what we're going to do is we're going to do a limit. If we start recording those slopes, like maybe this slope right here, this is an approximation, it's not the best one. Maybe the slope of that line is -2. Then maybe here it's like -1. Then here maybe it's -7/8. And then it's getting closer and closer to maybe the actual slope of the tangent line. Maybe that's -0.5. Okay, whatever it is. I'm just kind of guessing on that. But as we move it closer and closer, we keep recording these slopes. What's the slope of the blue line now? We write it down. What's the slope of the blue line now? We write it down. That's a limit, and we can see that it's approaching a number. The slope of the secant line could never go past the actual slope of the tangent line, right? That's the most it's going to go to. The slope isn't going to go more than that. So that means it has a limit. So we find the limit as h goes to 0. Okay? Eventually, that means that number means when the points coincide. And then if I turn off the tangent line, you can see the secant line is the tangent line. So that's how we find the slope of the tangent line. We're actually going to find the slope of the secant line over and over and take the limit as h goes to 0. So we're going to find what that slope is approaching. So that's that idea. Let's see if we can do a little bit of practice with this. Okay, so we were speaking about formulas in general. Now we're going to have a specific example. Suppose your function is this polynomial here. They want you to find the limit as h approaches 0 of that. We'll call it the difference quotient. Okay, so this thing is called the difference quotient. Why is that? I just want to talk about that for a second. Quotient means that you're dividing, right? So we clearly have a quotient of two things. We have a division bar, Difference means what are we doing in the numerator? We're subtracting two things. That's how we find the change in y. And in the denominator, we're subtracting two things. We already subtracted them in the denominator and we simplified it to h. In the numerator, we can't subtract them until we actually get the y values, plug in those x's, get our functions, and then get our expressions. Then we can go ahead and subtract them. So in the top, we will be taking the difference. In the denominator, we already have taken the difference. So just to point that out, that's called the difference quotient. We're doing the limit as h approaches 0 of the difference quotient. I'm going to push that difference quotient idea a lot because it's going to come back in the second half of the course to help with your understanding in the inverse operation. So that's our difference quotient, and it's really a slope. So suppose this is your function, find this. We've done this already, to be honest. You've been doing it in the limit section. So we like to do this in parts. F of x plus h. I already have f of x, right? They tell me what it is. So that's that part taken care of. I got to figure out what the f of x plus h part is. So f of x plus h means I'm going to rewrite this function, taking the x out, and replacing it with this expression, x plus h, goes in for x and goes in for x. That's all that happened here. So I get x plus h squared and x plus h. All right, so that's my f of x plus h. You can simplify this now or you can do it later. I'm going to go ahead and do it later. So now I've got my pieces that I need to find the limit of my difference quotient. So I'm going to go the limit as h approaches 0 of f of x plus h. That's this expression, right? So negative x plus h squared minus 4 times x plus h plus 1 minus f of x. F of x is this expression. I'm going to get rid of some of these circles and stuff that I'd been writing. So f of x is this expression. So minus x squared minus 4x plus 1. All over h. So if we want to find this limit, I'm going to try direct substitution. I'm going to notice that I get 0 in the denominator already. So I know it's undefined. You're going to get 0 in the numerator for these. It's just always going to happen when we're doing difference quotients. Okay, so you don't have to try direct substitution right away. You will always get 0 over 0. We're going to simplify. This one seems to be one of those factor and solve and cross off a common factor. So before I factor this, though, I have to multiply everything out. So it's negative, and I'm going to do x plus h squared is x squared plus 2xh plus h squared. I'm going to distribute the minus 4, or the negative 4, so it's going to be minus 4x minus 4h plus 1. Then I'm going to distribute my minus sign, so it's plus x squared plus 4x minus 1. Now I can distribute this minus sign. Negative x squared minus 2xh minus h squared minus 4x h plus 1 plus x squared. I don't need to be repeating what I'm writing. All over h. So now if you recall, I need a little more real estate here, so I'm going to cheat. Sorry. Give me a sec. All right, so now if you recall when we were doing these, I want the h in the denominator is my problem. I want to cancel that out. So what I need to do is I need to factor an h out of the numerator. So that means anything that doesn't have an h in it probably cancels. So I have a minus x squared, a plus x squared. That has a h. Minus 4x does not have an h, so there must be a plus 4x. Plus 1 doesn't have an h in it, so there must be a minus 1. So now I'm going to rewrite this thing, and at the same time, I'm going to factor an h out of all of these terms that are left. Okay, so I'm going to write h times minus 2x when I factor the h out of it, right? Minus h when I factor one of the h's out. Minus 4 when I factor the h out. All over h. Now that I factored out an h, I could cancel that factor. So that's going to be equal to the limit as h approaches 0 of negative 2x minus h minus 4. So the problem was the h in the denominator. That problem has been dealt with. So now I can do direct substitution. Remember, I'm not plugging into x. I'm solving for when h approaches 0. That's that distance between the x values goes to 0. So I plug in for h, and I get 2x minus 4. You're going to get x's in these answers, okay? So that represents the slope of the tangent line. It's weird because it's got an x in it, but that represents slope. All right? So we're going to call this thing the derivative, this function that we get, okay? And we use f prime of x as the notation. So it's called f prime of x. That's what we say. It's not a 1. It's like a quotation mark. So that derivative f prime of x of the function f. Okay? So now let's see what this represents in terms of the graph of f. So in this case, if f of x was, what was our original f of x? Negative x squared minus 4x plus 1. That means the derivative f prime of x is equal to negative 2x minus 4. Oh, so I should have a negative sign in there. I forgot it. This is negative because it was negative right there. So what this is a function itself used to find the slope of the tangent line. So a slope of a line is just a number. Slope is 3 or negative 1/2. So what the heck's going on here? Why does it have an x? Why is it a function? Okay, so we're going to take a look at that. So I have a Desmos made here for our function. So you can see that here's our function and here's some points on the graph, okay? This is that function that we're dealing with now. I put it in as the negative x squared minus 4x plus 1. I have the tangent line graphed here. So you can see that here's a tangent line at that point, at the x value 1.16. That tangent line has a slope, but what happens if I move the point? Right? The tangent line changes its slope. You have a new tangent line, right? So the slope at this point, if I draw the tangent line at that point, that slope is different than that slope. That's why the derivative is a function. It's got to account for that change. I can't just say the slope of the tangent line is 4 because it's 4. Maybe it's 4 like right here, but that's it. Okay? It's different. So every other play, if you move it, the tangent line is different. So notice it only touches the curve at one spot. Okay? So that's what's going on here. That's why it's got a derivative. That's why it's got an x in the derivative. Let's take a look at this. Like at this x value right here, right at the top of the graph, what would you say the slope of that line is? That slope is 0. Now, what x value are we at here? What's the point of tangency? It has an x value of negative 2. Let's go back to our derivative for a second. If I plug negative 2, that's the x value we're currently at, into our function, our derivative function, what do I get for an answer? I get 4 minus 4, I get 0. That's because when you're at an x value of negative 2, what's the slope of that line? 0. The derivative figures that out for you. Let's look at right here, let's say. What if I'm at an x value of negative 3? What would you guess that slope to be? It's definitely positive slope, right? And it looks like it goes up 2 and right 1. That's what it looks like to me. So I'm going to say that that slope of that line is a slope of 2. Let's check our derivative function. At the x value negative 3, if I plug negative 3 into my derivative, what do I get? I get 6 minus 4 is 2. So it's telling me that the slope of that tangent line is 2. So remember that it's kind of a neat thing. It's got an x in it because it's telling you the slope at any point. If I stop here, if I plug that x value into the derivative, it's going to tell me the slope of the line right there. And the slope of the tangent line, you have to remember, is just really a visual representation of how fast the graph itself is changing. We know at that point, that graph has got a negative change, right? Because it's going downwards. That's why the slope of the tangent line is negative, and that's what we're going to think of it as. All right, so that was a lot of kind of theory there. We're going to just start doing some stuff in practice and working with this and see what happens. And I apologize, this video is going to be long, but it's probably the most important video this year because it's the kind of the start of our whole thing here of calculus. So this is the first big idea in calculus. The idea that with a limit, we can find the slope of a line even though we only have 1 point. That's an amazing thing. Slope, we always need 2 points. Not anymore. The derivative finds the slope with only 1 point. So that's kind of the magic of calculus. We'll talk more about this in class, why it's so amazing. All right, so we're still working with the same function here now for the rest of this page, okay? It says the graph is pictured below. So there's our graph. Complete the chart for the indicated x values and f prime of x. So it's reminding us that if our function up here is this guy, our derivative that we got was this through that limit process, okay? So what they want us to do here is what? Find the value of f prime of x. So we're going to plug -4 into the derivative. That's what we were just sort of doing, and find out what that tells us. All right, so we have f prime of -4. That means we're plugging -4 into the derivative, right? We get -2 times -4 minus 4. We get 4. What does that mean? 4 would be the slope of the tangent line when our point of tangency has an x value of -4. Now we do f prime of -2. We actually looked at this one, I believe, on the graph. We did. So if we plug in -2 into our derivative, we get 4 minus 4 is 0. That means that's the slope of the tangent line of the tangent line when the x value at our point of tangency is at -2. And then similarly, f prime of -1 is going to be -2. That's going to be the slope of the line at that point. Okay, so now it says use a ruler. I don't have a ruler, but I can't use a ruler on this thing. Well, I guess I can, but I don't have one. So they want us to draw those tangent lines. So at x equals -4, so here's a point of tangency. If I draw that line in, I'm going to cheat a little. Over here, I know that the slope has to have 4, so I can go up 4, 1, 2, 3, 4, and over 1. That's the slope of 4. And then down 4, 1, 2, 3, 4, and over 1. If I kind of connect those 3 points, right, there's my tangent line. And you can see I built it, kind of did it backwards. I built it to have the slope it's supposed to have, but you can see that's how it works. At -2, if I draw the tangent line, you can see that it has a slope of 0. And at -1, which is right there, it's going to have a slope of -2. Whoops, it didn't quite touch, but there it is. Okay, so we did the ruler part. By investigating the graph, what does it appear that the derivative function represents in terms of the graph at the given values of x? So the value, I've said this a bunch, but we're going to kind of make sure we summarize it, of the derivative f prime of a represents the slope of the tangent line drawn to f of x, our original function, at x equals a. We call this thing evaluating the derivative, right? You have the derivative and you're plugging in an x value to find out what the actual value is at a specific point. That's called evaluating the derivative. When you plug an x value into a function, we say you're evaluating the function. So now when you plug an x value into the derivative, we're going to say you're evaluating the derivative. All right, so we just came up with the definition for the derivative, and it's based in limits. So a lot of the limits properties are going to apply to, all of the limit properties are going to apply to the to derivatives as well. Derivative f prime of x is a function results from the limit as h approaches 0 of the difference quotient, f of x plus h minus f of x all over h. That's called the difference quotient. And that can be used to find the slope. Remember, slope just means rate of change. When we're not talking about graphs, we're going to be talking about rate of change of any tangent line drawn to the graph of f. All right, so we're going to do some practice with this definition and evaluating at a point. So find the equation of the tangent line to f of x at each of the points below. Then draw the graphs of the tangent lines on the grid above where f of x is graphed. Okay, so we've got the equation of the tangent line at x equals 4. Now, they're talking about f of x, so remember on this whole page, we're referring back to this function. So it's negative x squared. I'm going to just write it up here again. Minus 4x plus 1, I think it was. Yeah. So we want the equation of the tangent line. So now we have to go a little bit further. Okay, so first we want to find the point of tangency. To write the equation of the line, we need a point and we need the slope. So to find the point of tangency, we already know the x value of that point. We need the y value. It's on the curve, right? If it's tangent, it means the point is on the tangent line and the point is on the curve f of x. So that's we're going to use that to our advantage. So we're going to plug the x value into the original function to evaluate to get the y value of this x value. So we're going to say it's negative 4 squared minus 4 times negative 4 plus 1. We should get 16, negative 16 plus 8 plus 1. Sorry. 1. I don't know why that was so hard for me. All right. So that's our point, our y value of our point. So I'm going to collect these as a point. Our point of tangency is negative 4, 1. That's the first thing we need to write the equation of the line. Now we want the slope of the tangent line. Those are the two pieces of information we need to write the equation of the tangent line. The slope of the tangent line at negative 4 is going to be if we plug negative 4 into the derivative. So if we plug negative 4 into the derivative, we're going to end up getting 4. We did that up above, so I'm not going to go through that. We're going to kind of highlight that information. With those two pieces of information, I can now write the equation of the tangent line. So we have y, we're going to use point slope form. So y minus the y value, which is the 1, equals the slope m times x minus the x value, which is negative 4. So minus a negative 4 becomes a plus 4. We'll leave it in point slope form. That is the equation of the tangent line. Then it says, then draw graphs of the tangent lines on the grid above where f of x is graphed. So we've already kind of drawn it, but I think they want us to actually graph it the way that I cheated. So like this would be the point of tangency, right? So graphing from this, I would use the point negative 4, 1, and then I would use the slope of 4 to go up 4 and right 1. I already sort of did that. I cheated, right? Up 4 and right 1. So they want us to do that now. You're supposed to see that that line is the line you drew with your ruler. So we'll skip that part for now. You are going to pause the video here and do the next two here and see if you can get them. All right, Aiden, I'm calling you out. You better have paused it and done this. I'm watching you. I wanted to highlight the information you needed here. All right, so there's your two answers. You can pause and check those if you like. See if you got them right. Moving along. This is important. We're just talking about what the derivative means graphically today. So I want to focus on the slope of the tangent line. When I say derivative, when you say derivative, graphically, we mean slope of the tangent line. Those are interchangeable things. So slope of the tangent line means derivative. Derivative is slope of the tangent line. It's all the same thing. I'm going to probably be using those phrases interchangeably. And when I say one, I'm always going to follow up by saying the other for right now, so that you get used to just learning the vocabulary. Now that we understand what it means, let's practice. So let's see if we can just find some derivatives using the limit of the difference quotient. And again, you've sort of already done this. In limits, we were preparing you for this all along. You didn't know it. Really, that's just solid teaching, to be honest with you. I mean, it really has nothing to do with you guys. It's more that I'm fantastic. So, I don't know. Anyway, let's figure this one out. So f of x plus h means I rewrite my function, but I plug in x plus h for x. So I'm just taking this and I'm rewriting it here. I'm removing the x, and in its place I'm putting x plus h. I don't want to kind of write this out in separate steps. We got to get good at just doing it as we go. So that's the f of x plus h part right there. Matches this part. Minus, now we'll do the f of x part. I'll make it color coded so we can kind of see where the parts come from. So minus f of x, so that's going to be 2/3 x plus 3. Okay, why the parentheses? Because that minus sign, you got to make sure you distribute it all over h. So now we can start simplifying this difference quotient, because direct substitution will not work right now. We've got to cross out that h on the bottom. So I'm going to distribute my 2/3 and distribute my minus sign. So anything that doesn't have an h in it better go away. 2/3 x minus 2/3 x. 3 minus 3. Perfect. So now I'm left with 2/3 h over h. I don't even have to factor. It just cancels out. So now I've got the limit as h approaches 0 of 2/3. So I can do direct substitution. And of course the limit of a constant is just itself. So the derivative here is 2/3. That's interesting because this one did not have an x in it. Sometimes it won't. We're going to talk about why that is in a little bit. It was just a constant. The derivative was a constant. Let's do the same thing here. So the limit, I like to write out the definition first, of f of x plus h minus f of x all over h. So that's the limit as h goes to 0 of our difference quotient, which again is really just slope. So I'm going to say the limit as, I'm supposed to say h goes to 0. The limit as h goes to 0 of f of x plus h. So again, I write my function, I remove the x's out of it, and I put in its place x plus h. That's what f of x plus h is. So this part replaced this part. Minus f of x, 1/2 x squared minus 2x plus 3. That part, let's go purple, is that part there. Don't forget your parentheses, right? So that negative sign gets distributed all over h. Direct substitution does not work because I'm dividing by 0, so I got to cancel that h out of there. I'm always writing the limit until I actually do direct substitution. So on top, I'm going to square the x plus h. I'm going to distribute the -2 and distribute the minus sign. Now I got to distribute the 1/2. That's 1/2 x squared plus 2x minus 3 all over h. Anything that doesn't have an h better cancel. 1/2 x squared minus 1/2 x squared. xh has an h. 1/2 h squared has an h. Minus 2x plus 2x. Plus 3 minus 3. Yes, it all canceled. We're good to go. When I write this step, I'm also going to factor out the h. So the xh becomes just an x. The 1/2 h squared becomes just 1/2 h as I take an h out of each part. The minus 2h becomes a minus 2 all over h. I can cross off the problem. I can then do direct substitution in for h, so I don't need to write limit anymore because I'm plugging in 0 for h. And I end up getting x minus 2. So the derivative is x minus 2. Notice that this derivative has an x in it, and the other time this one here did not have an x in it. So it doesn't always have to have an x in it. So that's kind of what we're saying down here with this question. So what's happening? They're different because one is just a constant function, 2/3, and the other one is a function that has x in it. So why does that occur? Well, if we analyze our original function, what kind of graph is 2x plus 3? Well, it's a line that has a y-intercept of 3 and then a slope of 2. So maybe it looks like that. If that's our original graph, how the heck do you draw a tangent line to a line? You kind of can't, right? The tangent line is supposed to describe what's the slope of the graph at that point. Well, the thing about a line is it has constant slope. The slope of this line is always 2/3, no matter what x value you're at. So when your original function is a line, the derivative is always just going to be whatever the slope of that line is. So that's what's going on there. And this guy, sorry, is a parabola that opens upwards. I don't know where it's located. I'm not going to try to figure out the vertex, but what's important is it's a parabola. And now the slope of the graph at any given point changes. If I make that my point of tangency, I've got a negative slope. How about if I look over here, I've got a positive slope. So the slope is changing. At any given point on that graph, the slope changes. That's why it needs to have an x in it to account for that change. It can tell me the slope no matter where I'm located. So how do I want to write that out? I don't want to write, I don't want to write all that out. If we were just to summarize it, we would just say, well, in the first function, too bad they're both named f. In this function, the derivative is a constant because f was a line, and the tangent line to a line is just the line itself. You could say something like that. And so the derivative has to be the slope. So I'm not going to say all that. I would just say that that's sort of the difference of what's going on there. We could say in the second function, I don't even want to, I'd set it, you can write it if you like. The second function has an x in it, its derivative, because the slope's changing. So let's look at this next thing. So we're, again, just using the f here to find f prime. So we're going to go the limit as x, keep doing x, as h approaches 0. Sorry, this is going to be an hour video. Hopefully it's done before an hour. F of x plus h. So I'm going to rewrite this function, take out the x, and put in an x plus h. So that part is f of x plus h, which is that part. Now I got to do minus f of x. I don't need parentheses because there's already parentheses in the square root thing all over h. So this part right here matches that part. All right, so let's simplify this thing. So how the heck are we going to solve this limit? We do direct substitution. We know it's over 0. This is going to be, this is why we practice this. I'm going to cheat again here. This is why we were practicing rationalizing the numerator. Well, that didn't work. Let's try that again. Okay, I give up. We're going to multiply by the conjugate, and it's going to run over into the other side. It's not going to work out. Why is it doing that to me? All right, I'm going to get mean. Let's pull it down here and see if it'll stay. All right. So now, how about that? All righty. So I want to multiply the top by, oh, I need a smaller, if I want to zoom in that much. Okay, we're going to multiply the top by its conjugate pair. And the bottom by that. remember the h on the bottom is causing the problem. We want to cancel it out. So we're not going to multiply out the bottom. When we multiply the conjugate pairs up top, I get x plus h plus 2 minus x plus 2. I multiply the first times the first, the square root just drops. The last times the last, the square root drops. But remember, it's a negative times a positive, so I get a negative. So that's what I get when I multiply the tops. On the bottom, I'm not going to multiply it out at all. I want to cancel that h, so I've got to leave it factored out front. Now I can simplify the top. I've got x minus x. Well, I guess I'll write it out. X plus h plus 2 minus x minus 2 all over h times so now in the numerator, anything that doesn't have an h in it should cancel. X minus x2 minus 2. So I'm left with h over h times the square root of x plus h plus 2. Whoops, no parentheses there. Plus the square root of x plus 2. This h was the problem. It now cancels or divides out. So I have 1 over. So now I can do my direct substitution. I plug in 0 for h. If I have, I'll just call this a thing. I have one of those things plus another one of those same exact things. I'll now have 2 of those. That's how we add those. If they're exactly the same, I could actually add them. So f prime of x equals 1 over 2 times the square root of x plus 2. That's our derivative for that function. Okay, let's look at the next one. F of x plus h means I take out the x and I replace it with x plus h. So that's what I did here. I just recopied that, removed the x, and put x plus h in its spot. So that's f of x plus h minus f of x all over h. Direct substitution fails here because I have 0 in the denominator. This is a complex fraction one. So I need a common denominator. So I'm going to go x plus h plus 2 is one denominator and the other one's x plus 2. That's going to be my common denominator. So up here it's 3 times x plus 2 and my numerator here is going to be 3 times x plus h plus 2 all over h. Now I can combine that numerator. That was weird. Limit as h approaches 0. So it's got x plus h plus 2. That's my denominator. I add or subtract the numerators. I'm going to distribute the 3 as I go as well. So 3x plus 6. Now here, when I distribute the 3, I'm also distributing that negative sign that's kind of attached to it. So I'm going to get negative 3x minus 3h minus 6 all over h. I've got 3x minus 3x is 0, 6 minus 6 is 0, so I've got negative 3h over x plus h plus 2 times x plus 2 times, instead of dividing by h, I'm going to multiply by 1 over h. Remember, that's h over 1. H on the bottom was the problem. It now divides out right there. So I've got negative 3 over x plus h plus 2 times x plus 2. If I do direct substitution, I don't have to write limit anymore. I plug in 0 for h. So f prime of x equals, I'm writing this gigantically, So the derivative, which means the slope of the tangent line at any given x value, if I plug in the x value, I get the slope of the tangent line. It's that function right there. So for this function f, its derivative is that. Actually, if you notice, that derivative looks sort of similar to the function itself. All right, so now they actually want you to find the equation of the tangent line at an x value of 7. So this is this function f. So how do we write the equation of the tangent line? Well, we're going to write it in point-slope form, which, remember, is y minus y1 equals m times x minus x1. And what you need is you need a slope for that, and you need a point x1, y1. So we're going to first find the point of tangency. I'm going to abbreviate in here, but you really can't on a quiz. You got to write out point of tangency if you're trying to do that. That's when I plug the x value 7 into the function. So the point of tangency is 7, 3. So that's this thing here, right? I have my point. Now I want to find the slope of the tangent line. I'm going to do f prime of 7. I'm going to plug 7 into the derivative. So I get 1 over 2 times the square root of 7 plus 2. I plug that into the derivative here, right? So I get 1/6. So now I'm going to use this piece of information, the slope and the point, to write the equation. So the equation of the tangent line is going to be y minus 3 equals 1/6 x minus 7. Now they want us to do it for this guy. All right, so it's at the x value of 1. So we first want to find the point of tangency. That's going to be f of 1. We plug it into the original. We get 3 over 1 plus 2. We get 1. So it's the point 1, 1. We need the slope of the tangent line. We're going to plug 1 into the derivative, which was negative 3 over x plus 2 squared. X plus 2 squared, yeah. All right, so we're going to say negative 3 over 1 plus 2 squared. We're going to get negative 3 over 9. Negative 1/3 is our slope. So now we're going to use the point of tangency and the slope of the tangent line to write the equation of the tangent line. So we got y minus 1 equals negative 1/3 x minus 1. Alrighty. Using a graphing calculator, graph each of the functions above and the equation of the tangent line that you found to verify your work. So you're gonna do that right now. So you're gonna graph in y1, for instance, this guy, and then in y2 you can graph this guy, and you're going to see that it's the tangent line at that point. It's the point where it touches once. Once I get my license, I'm waiting on a license from a TI emulator. My trial version ran out. I'll be doing that in the videos. So I'll use the emulator, but for now you can do that calculator work on your own. All right, we're almost there. Last couple things. So we found derivatives of several functions and evaluated at certain x values. Let's look back at our work and complete the table below. So I'm going to say this is open for you to do. And we can talk about this at the start of class. Okay? So I want you to just kind of look back, and this sort of gathers your information, and this is a very good summary here. Okay? This one is a little bit interesting. It's an alternate definition for a derivative. So we're going to talk about that right at the start of class. And then we'll talk about this derivative and alternate form of the derivative. 54 minutes, not bad.